Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 40 and we are in lecture 19, part A, and we are moving into section 8.2 in the text, and this is dealing with two means. And so we're going to do, the first case is paired data. So we're going to take two samples and they're paired, the values are paired, so we're going to take the difference between the two observations on the same unit usually. And so we're going to do hypothesis test for mu sub d, the difference. So, test about the mean difference based on paired data. So, some examples here are the effectiveness of a new diet. For each subject, we observed X is the weight before, Y is the weight after, and the D would be Y minus X, let's say. So, hopefully it'd be negative, not positive, right? Lose weight. Or we could compare cancer treatments. Here we do not have the same person and two measurements, but we could pair them by the stage of the disease. So if they're in stage 1 of cancer, we could compare those. If they're in stage 2, we can compare those. So apparently that's been done. All right. We're going to look at a little more obvious cases of paired data where the measurement's on the same individual. So these are the assumptions. A random sample of n members is selected from a population, and a pair of measurements, that's two, pair, is recorded for each member. This could be height and weight, so they're related. But that would be more for correlation. That wouldn't work so much for paired differences. So let's say it would be the height when born, the height when they're 18 years old. Okay, so you could do a difference, how much they grew in 18 years. Okay, something like that. All right. So the pairs, X and Y, X1, Y1 up to Xn, Yn, they have to be independent, and they also have to be identically distributed, and they have to have a common bivariant PMF or PDF, and we'll call that f of xy. So what are the implications of these assumptions? We have these IID pairs, which implies the within pair differences d sub I equals y sub I minus x sub I equals 1 to n. They're IID random variables with a common mean. This common mean is mu sub d, and again, we could calculate that, or it is the expected value of the d sub i's. And they have a common variance. Okay? So sigma sub d squared is equal to the variance of d sub I. In other words, d1, d2 up to dn represents a random sample of size n. So the differences are a random sample. And from a population with mean mu sub d and variance mu sub d, or sigma sub d squared. So we can calculate d bar and the sample mean and the sample variance S sub d squared from a sample. So here is an example. We have n equals 10 ore samples. So these are metal, so ore that's mined, and they're randomly selected, and the percentage of iron content in each sample is measured by two different methods. So that's another way to pair it. And so here are the data. Okay? So we have the sample 1 through 10, so n is equal to 10. And we have the percentage of iron using method A, the percentage of iron using method B, and we're going to subtract B minus A. And so D is here. Okay? Now to calculate D bar, we need to add up all the D's. So we get 0.13, that's the sum of D, which is what I've written here. Okay? Well, in order to calculate the variance, we need d squared. So I've squared each of the differences here, added those up. This is sum of d squared. So d bar is going to be the sum of d's divided by n, so that's 0.013. S sub d squared is given by this formula, and that's going to be 0.00389. I'm not rounding at this point. Okay? So we want to test at a significant level of 0.05 whether the two methods differ in the assessment of the mean percentage of iron in the ore samples. and the data is from an approximately normal distribution. This has to be the case if n is less than 30. Otherwise, we can't use this method, right? We have to use a different method. So the hypothesis statement, this is going to be mu sub d is equal to 0. Why 0? Because we're saying that there's no difference. That's going to be mu 1 minus mu 2 equals 0 implies that the mean of 1 equals the mean of 2. Okay? Same thing. Different ways of writing the same thing. So if there's no difference, if these are the same, the measurement method is the same, then the difference is going to be 0, and that difference is mu sub d. Versus, let's see, we're going to say mu sub d is not equal to 0, alpha equals 0.05. Okay? So the test statistic is going to be given by t observed, which is, because we have s instead of sigma, we have to use this. Again, in real life, it's very rare that we have sigma or mu. So the square root of n, which is 10, d bar was 0.013 minus mu sub d is 0 over s sub d, which was 0.00389. But square root, don't forget to square root. This is SD squared. We need SD. So this is going to be the square root of 10 times 0.013. Oops. The square root of 10 times 0.013 divided by the square root of 0.00389 gives me 0.6591. Okay. Since this is t, I'm going to round it to 3 decimal places, so 0.659. The critical region, this is going to be, since this is going to be the absolute value of t observed is greater than t naught, which is t sub alpha over 2. So alpha equals 0.05 divided by 2 is 0.025. N is going to, degrees of freedom is going to be n minus 1, which is going to be 9. So in order to get t sub alpha over 2, I need 9 degrees of freedom, and I'm looking at t sub 0.025 with 9 degrees of freedom. So the t table, 0.025 is here. 9 degrees of freedom is here, 2.262. So this is 2.262, and the absolute value of this is still 0.659. This is not true, so we do not reject H naught. And in this case, that's a good thing. We want the methods to be the same. So there does not exist sufficient evidence to support the claim that the two methods differ in the assessment of the mean percentage of iron in the ore samples at a 95% confidence level using a random sample of n equals 10 ore samples. Let's determine the p-value for the test in part A. Now, we used t observed, right? So we have to, we won't be able to find an exact value. We'll have to find a range of values. And so our t observed was 0.659, and the degrees of freedom is 9. So we're looking at the table with line 9 for degrees of freedom, and we want to see between what two values does our test statistic value fall. And so for 9, we want to see, and 0.659 is going to be between these two values. Now, we have to be careful. This is a two-sided test, so we're going to look at this number, and that is 0.40 and 0.25. However, remember that this is for a one-sided test, so we're going to have to multiply these numbers by 2. So it's going to be So we've got 0.25 and 0.40, and so that's going to be 0.50 and 0.80. So our p-value is between 0.50 and 0.80. So there's absolutely no value of alpha that we would want to use where we would ever reject the null hypothesis for this problem. Okay? All right. Now, we're going to keep everything the same except we're going to change n to be greater than 36. Now, I will tell you that in practice, many people still use the t-table until you get up to like 100 or so. Most people will continue to use the z-table. But for us, in this class, since the book tells us that we can use z for n greater than or equal to 30, we will do so as well. All right? So the only thing that changes is our value of n, and now that changes our test statistic from 0.659. Now we have 1.25. So our critical region, we're going to reject H naught if the absolute value of z observed is greater than z naught. Okay? So z observed is 1.25, and we need to find z naught. And z naught, remember, it's going to be z sub alpha over 2, where alpha is 0.05. So this is going to be z of 0.025. And so that means this is going to be 0.0250. And, or we could look in the table where we're looking at critical values at the bottom of this first page. And so 0.05 is here. And z of alpha over 2 is going to be 1.96. Okay? So 1.96. That's a fast way to find it. And so this is going to be 1.96. So we want to know if 1.25 is greater than 1.96. It is not. This is not a true statement, therefore we do not reject H naught. So there does not exist sufficient evidence to support the claim that the two methods differ in the assessment of the mean percentage of iron in the ore samples at a 95% confidence level using n equals 36 ore samples. Okay. Find the p-value. So now we have, it's a two-sided test. It's z, so we want to find, so we have z is 1.25. We want to find the probability away from 0. For this. So we want to find what this is, but it's a two-sided test, so whatever that is, we'll have to multiply by 2. So 1.25, we want greater than, so we'll go to the second table, and 1.2, we start with 0, 1, 2, 3, 4, 5. It's going to be 0.1056. So this is 0.1056, but this is a two-sided test, so we don't care that it's positive. We just want the probability that it's that far away from the mean. So the p-value equals 2 times 0.1056, which is 112. Yep, I believe so. I will make sure of this by using the calculator. 0.1056 times 2, yep, 2112. Okay. So again, if we use the p-value method, p-value less than alpha. So alpha is 0.05, 0.2112. We do not reject. Same conclusion that we had with the critical value method. Okay, that's it for this video. If you have questions, by all means, come to virtual office hours. If you need help before virtual office hours, by all means, email me, but make sure you email me a picture of the problem because I don't have that available usually, and a picture of your work so far so I can see how you're approaching things and help you better. Please take care of yourself, stay safe, because we hope to see you here next time.